In today's lesson, we're going to look at the end behaviors of graphs, multiplicities, and graphing polynomials today. So, let's take a look. Right here, we have functions, and if you guys notice, they are positive and they have even powers. Now, something to note about these is notice how their end behaviors of each graph. So as we go negative to infinity, the graph goes up, and if we go to positive infinity, the graph goes up. So we can make a statement when we have positive even powers, the end behaviors are gonna look like this, up and up. And we would describe them as, when we describe the end behaviors, we write this as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches infinity. So let's talk about that. If we look at either one of these two graphs right here, as x goes to infinity, or as x goes to the right, f of x, the y values, they go up, which is positive infinity. And as x goes to negative infinity, or to the left, notice how the graph goes up for f of x goes to infinity. So that's what the end behavior for positive even powers look like. Now, if we take a look at these functions, they're both even powers, but they're negative. So we have negative even powers right here. So if you guys take a look, their end behaviors look like this. Down, down. So to remember this, just remember the end behaviors just go down, down. And to describe this, right, as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches negative infinity. So when we look back at these graphs right here, as x goes to infinity or to the right, notice that f of x goes down towards negative infinity. And then as x goes to negative infinity, f of x goes down. F of x approaches negative infinity. So that's how we get those end behaviors for those. Alright, so moving on. Now if you guys take a look at here, we have odd powers, and we're going to be looking at positive odd powers and negative odd powers of functions. So if you notice that for all positive odd powers, this is what all of their end behaviors look like. So we have a down and it goes up. So as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x approaches negative infinity. So right, as x approaches infinity, so if it goes to the right, then f of x goes up. F of x approaches infinity. And as as x approaches negative infinity, going to the left, f of x approaches negative infinity, going down. So those are end behavior for positive odd powers. Now let's look at negative odd powers. If you look at the end behaviors, right? Up, and then it goes down. So To describe the end behaviors, we say as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches infinity. So as x approaches infinity, which means going to the right, then f of x approaches negative infinity, which is going down. And as x approaches negative infinity, f of x goes to positive infinity, which means going up. So that is the end behaviors for all the possible graphs that we will see. So now let's look at multiplicity. So multiplicity is how many times a zero appears at one location. So if we have the multiplicity of 1, in short, we'll denote it as this. Now, if you have a multiplicity of 1, that means the graph will cross through a 0. So let me explain. Let's say if you guys had this function, okay? F of x is equal to x plus 1. Well, we know that if we were to make this, or if we were to find a 0, we would know x would equal, will have to equal negative 1 for it to be a 0. Now, if you saw a graph of this, we know x is equal to negative 1. So that means the 0 would be right there. And it will cross, we will cross at that 0, just like so. So if you have 1, 0, then you will notice 1, 0, a multiplicity of 1, then you will notice that the graph will just cross through a 0 right there. All it does is cross. So that's multiplicity of 1. Multiplicity of 2. In short, it would be noticed as multiplicity of 2. This bounces off a 0. So first, if it's multiplicity of 2, that means at that particular 0, there are 2 zeros located at that point. So let me show you an example. If we had f of x is equal to x minus 2 squared, notice that this is the same thing saying x minus 2 times x minus 2. So that means if we were to locate a 0, x would have to equal 2, but there are 2 of them. There are 2 zeros at 2. And if you were to look at a graph, at 2, the graph is going to bounce off at that 0. So, just like that. Notice how that graph, right, it just bounces off that 0 at 2 because it's a multiplicity of 2. And lastly, we're going to look at multiplicity of 3. And in short, it's called multiplicity of 3. So when you have a multiplicity of 3, meaning there's 3 zeros at that one location, it will slide through the 0. So if you had f of x is equal to x plus 1 to the third, remember this is really saying x plus 1 times x plus 1 times x plus 1. And if you were to find a 0 in that, you would know x is equal to -1, and there are 3 of them. There are 3 zeros located at x is equal to -1. And then again, on a graph, this is what it would look like. Your 0 is at -1, and it's going to slide because there's a multiplicity of 3. So your graph will look like that. And if it's hard to see, this is what a slide looks like. Alright, so that is what multiplicity is. Now we're going to combine both what a end behavior is and multiplicities, and we're going to apply that to graphing polynomials. So let's look at this first example. Okay, so first we have to find our zeros. Alright, so I know x is equal to 3, x is equal to -2, and x is equal to 1. Now, I know, let's use blue. I know this x is equal to 3. That is a multiplicity of 3. Now, the reason why I know that is, if you guys look at the powers, right? This power represents how many of these guys there really are. There's 3 x minus 3's, which means that there's 3 zeros at x is equal to 3, which is why it's multiplicity of 3. Now for x is equal to -2, look at the power. There's 2 of them, so that means this is going to be multiplicity of 2. And x equals 1 just has a multiplicity of 1. You don't need to write multiplicity of 1 down, but you do need to write it down for multiplicity of 2 and 3. So we find our zeros, and the second step is to label any multiplicities. And now let's look at the end behavior of this function. So when you guys find the end behavior, right, we have to know what is the highest degree. Well, the degree of this one, the highest degree of that one is going to be of 3. The highest degree of this one's going to be 2, and the highest degree of this one is going to be 1. So, in total, we have this leading value or variable, it's going to be x to the 6. I'm just basically adding all my degrees together and noticing that this is going to give us x to the 6. And it's going to be positive because I don't see any negatives on the outside of the function. So x to the 6, that means that that is a positive even power. And if it's in positive even power, right, your end behaviors are going to look like this. So, label any multiplicities. The third is to identify highest degree. And the fourth step would be to find end behavior. And I forgot to mention this, but if it's multiplicity 3, you know it's going to slide. If it's multiplicity of 2, you know it's going to bounce. And you know if it's multiplicity of 1, it's going to cross. So this is all of the information you guys need in order to graph our polynomials. Now we will graph. So let us graph this. Okay, I'm going to label my zeros. So I see 1 at -2. From right here, right? I see a 0 at 1, which is right there. And I see a 0 at 3, which is right there on the graph. And now we can finally graph this. So graph your end behaviors. So here's your guys' end behaviors, right? You know this graph eventually, since it's the highest degree is x plus 6, is going to be up, up. So I'm going to do up and up. Now, I am following our multiplicities list. So let's first look at x is equal to -2. At x is equal to -2, this one right there. At x is equal to -2, you know this graph is going to bounce off. So I follow this, and I know it's going to bounce off. That's what a bounce off looks like, so this one's good. Now, the next one's going to be x is equal to 1. Here is x is equal to 1. I'll do a different color. Here's x is equal to 1. And we know the graph is going to now cross at that point. So, going down here, and I know it's going to cross it. I'll draw it better. You know it's going to cross. Okay? That one's done. Now the last one is x is equal to 3. Because notice that the next one coming up is x is equal to 3. And that one, you guys, is going to slide. So I'm going to curl this, and then I'm going to make it slide, and then I'm just going to connect it. And this is how you guys do a rough sketch of your guys' graph. So this one bounced, this one crossed, and this one slid. Alright, so that's the first example on how you guys are going to sketch your guys' polynomials. Alright, good. So there's example 2. Or sorry, that's example 1. Now let's do another example for example 2. Alright, so remember, first step is to locate your zeros, right? Find our zeros. Okay, so x is going to equal to 0. That one's coming from this one. X is going to equal -1. That one's coming from this one. X is equal to 2, coming from this one. And that one is a multiplicity of 3. Because notice the exponent right there, right? And then the next one's going to be x is equal to -3. Coming from there. And notice this one's going to be multiplicity of 2. So I'm going to write multiplicity of 2. Now, let's add all of our exponents together, because we have to find what the highest degree is going to be for this polynomial once we expand it. So, degree 1, degree 1, degree 3, and degree 2. Add those all up so we know we're going to get x to the 7th power. Now, find our end behaviors, right? Our end behavior for positive, I'll shorthand it, positive odd power, it is going to look like this. Alright? Oh, and I forgot to write what my multiplicities mean. So if it's multiplicity of 3, that means it's going to slide. And if it's multiplicity of 2, that means it's going to bounce. And don't forget, if it's multiplicity of 1, it's going to cross. So we have everything we need. Now all we have to do is just graph this potential polynomial. So let's get out our graph. I'm first going to write down our zeros. So I see one at -3 coming from there. I see one at -1 coming from there. And I don't know why this always closes on me, but I see one at 0. Gonna locate it right there. And I see one at x equal 2. Gonna plot that there. Alright, so look at your end behaviors. I know it's gonna look like this, and I know it's gonna look like that. I will drag this further up so that you guys don't get confused. Alright, time to graph. So, our first one that I'm looking at is x is equal to -3. I'll do a different color. Okay, right. X is equal to -3. That means it's going to bounce, right? Do you guys see that? At x is equal to -3, it's going to bounce. So, right there, and it bounces. Okay. Bounce. Now, the next one, right there, x is equal to -1, that means it's going to cross. So I know my polynomial right there is going to cross at that point. Cross. Now look at the next 0. It's at x is equal to 0, which is right there. That means it's going to cross there. So, cross. And then finally, when we reach, oh, not that one, when we reach x is equal to 2, it's going to slide. So, here we go. Gonna slide that, and that is what that graph is going to look like, okay? So, from these first two examples, you guys, 1 and 2, that is what it looks like to graph your polynomial in factored form, because notice that both of them are in factors, right? So that's how you guys graph when it's in factored form. Now, those are those two examples. Now, ooh, that's not good. I didn't erase it. Now we have ones like this, where you guys are gonna have to do it from standard form. Now, this is where, for the first time, you guys are going to graph it from standard form. Now, in order for us to graph it in standard form, notice that example 1 and 2 right here, you guys, those were all in factored form. So we can't graph a polynomial unless we put the polynomial in factored form, which means we're going to have to factor this guy. So, first thing I notice in this polynomial is I can factor out an x from each term. Now, I told you guys this before. I don't like having negatives in the front of my leading coefficient. So I'm going to factor out a negative x from both, because notice how all of them have an x variable, right? So I'm going to factor out negative x. So negative x all out of x to the 4th plus 2x to the 3rd minus 11x squared minus 12x plus 36. Alright, and sorry, both of these should have a function. Function is equal to that, and f of x is equal to that. Alright, so next, we have to use rational root theorem to factor that out. So, this one, that's your guys' p, and here, well, not really there, but right there, which is 1, that's your guys' q. Alright, so p factors is plus or minus 1 and 36, plus or minus 2 and 18, plus or minus 3 and 12, plus or minus 4 and 9, and plus or minus 6. Those are all the factors of 36, and now we got q factors, which is plus or minus 1. So we gotta find our p over q, which is gonna be plus or minus 1, 2, 3, 4, 6, 9, 12, 18, and 36, all over plus or minus 1. So all of these over that plus or minus 1, so we're going to get plus or minus 1, pretty much all that whole line back. So remember, these are all our possible roots. Now it's time to go and try to do synthetic division with this. Alright, so synthetic division. I see we have a 1, 2, negative 11, negative 12, and 36. And remember, you guys, I'm getting it from these coefficients right there. So we have to test out a point. Let's try 2. 1, 2, 4, 8, negative 3, negative 6, negative 18, negative 36. Alright, great. Alright, so we found one root, which is this one. That's good. Now we have to do it again, right? Because we can't factor unless we have a trinomial. Alright, so 1, 4, negative 3, and negative 18. Now we need to try to find another one. Well, we already found that we got 2, so maybe let's try 3 then. 1, 3 times 1, 3, 7, 7 times 3, 21. Well, that's not going to work, so I'm not going to go any further with that one. Let's try negative 3. 1 times negative 3, negative 3. 1 times negative 3, negative 3, negative 6. Oh, nice. So, we found 2 roots. Now, let's put this into polynomial form. So, whoa. Don't forget, remember at the very beginning, we factored out a negative x, so we have to write that. So we have negative x times, here's this root. Don't forget this root, right? So we got x minus 2. Don't forget this root, x plus 3. And now we have all of this right there. X squared plus x minus 6. All of that is equal to 0. Now, we just factor out that using your guys' x method. Negative 6 and 1. Right, negative 6 is negative 6 times 1. That's how we got negative 6. And the 1 on the bottom, this one, comes from that coefficient right there, which is 1. So I know 3 times negative 2 will give me negative 6, and when added gives me 1. So luckily, a is equal to 1 right there. So those are my factors for that trinomial. So negative x times x minus 2 times x plus 3 times x plus 3 times x minus 2. All this is equal to 0. So notice my zeros are x is equal to 0, x is equal to 2, x is equal to negative 3, x is equal to negative 3, and x is equal to 2. Alright, so there's that. Now notice that we have x equals 0. I'm going to rewrite it. X equals 2, but notice that there's 2 of them. So that means multiplicity of 2. And look at here, we got 2 negative 3. So x equals negative 3, multiplicity of negative 3. So we found our zeros. And now remember, if it's multiplicity of 1, it crosses. If it's multiplicity of 2, it bounces. And if it's multiplicity of negative 3, it slides. So, now you have to find your end behavior. Well, sorry, first we find an end behavior, you have to find your highest degree. Now, if we look back at the original problem, here is the highest degree. So, and look, there's a negative in front of it. So that means we're going to have negative x to the 5th, which is a negative odd power. So just like in the notes, right, from before, if it's a negative odd power, that means your end behaviors are going to look like this. So now it's time to graph that. Okay, so the first one I'm going to graph is negative 3. X is equal to 2. And x is equal to 0. So those are our zeros. I'm going to write in our end behaviors, which is down, which is up and then down. And now we can finally make a sketch of our polynomial. Well, the first one is x is equal to negative 3, which is that one, right? Which means it's going to slide through there. So we got that. Now next is x equals 0. All it's going to do is cross. So it's going to cross. And then lastly, we have x is equal to 2, which means it is going to bounce. And I made a fatal error. If you guys take a look, I accidentally wrote, there's only 2 negative 3's. So I made a mistake because this shouldn't be a multiplicity of 3, it should have been a multiplicity of 2. So if you guys caught that from before, I'm sorry. So if it's multiplicity of 2, that means it's going to bounce. As you guys can see, one mistake like that, it could ruin the whole thing. So let's try this again. At negative 3, it is going to bounce because it's a multiplicity of 2. So here we go. At x is equal to 0, it's going to cross. And then at x is equal to 2, it is going to bounce. And then finally, my graph looks like that. So that one is a very huge process, as you guys can see, right? You're gonna have to factor out that polynomial, find all of your roots, and then graph the polynomial. So there's that example. Now we'll take a look at example 4. Alright, again, gotta factor this out completely. So, there's my P, there's my Q. So, P factors are gonna be plus or minus 1, plus or minus 1 and 6, and plus or minus 2 and 3. And my q factors are just plus or minus 1. Alright, so p over q is going to be plus or minus 1, 2, 3, and 6, all over plus or minus 1, and that's just simply plus or minus 1, 2, 3, and 6. These are all my possible roots right there. Now we gotta go and factor and try to find a root. Okay, so coefficients. Coefficients are 1, 1, negative 7, negative 13, and negative 6. So we gotta pick a possible root from there. I'll just pick 1, 1, 1, 2. 1 times 2 is 2, negative 5. That doesn't look good, so it's not 1. Negative 1 work. 1 times negative 1, negative 1, 0, 0, negative 7, 7, negative 6, 6. And there we go. There's one of our roots. Now remember, this is not a trinomial, so we have to go again. 1, 0, negative 6, negative 6. Negative 7, negative 6. Alright, so we have to go again. We tried 1, didn't work. Negative 1 works. Now we got 2, 3, and 6. Let's go for 2. 1, 2, 0, add 4, negative 3. Ooh, that was close, but it's not quite. Let's go for negative 2. 1, negative 2, negative 2, 4, negative 3. There we go. Alright. We found our two roots, and it's finally a trinomial, so now we can set up our polynomial. So x plus 1, x plus 2. Remember, it's the opposite of these, right? And then set up a trinomial. Constant, first degree, second degree, so it's going to be x squared minus 2x minus 3. All of that is going to equal 0. Alright, we gotta factor out that trinomial, so negative 3, negative 2, 3, nope, not 3, negative 3 and 1. And a is equal to 1, which means these are the factors of that trinomial, x squared minus 2x minus 3. So x plus 1, x plus 2, x minus 3, and x plus 1. So my zeros are x equals negative 1, x equals negative 2, x is equal to 3, and x is equal to negative 1. Now once we have our zeros right, this is where we write down our multiplicities of our zeros. So x is equal to negative 1 multiplicity of 2. There's 2 of them. X equals negative 2. And x is equal to 3. Multiplicity of 2, right? That means it will bounce. And these will just cross because they're both multiplicity of 1. Now, recall our original equation, right? I'm going to erase this so you guys can see. Now we have to see what the highest degree was. Remember, it was x to the 4th. So that means, and it's positive. So highest degree is going to be x to the 4th, and that's a positive even power, which means positive even end behaviors are going to look like this. We got our multiplicities, we got our end behaviors, and our zeros. Now it's time to graph. Okay, so let's plot our zeros. We got one at negative 2, negative 1, and we got at 3. And here's our end behaviors. Okay, the first zero we're going to encounter is x equals negative 2. So, right, it's going to cross there. So, cross. now we have -1. And at -1, we know it's going to bounce. So cross and then bounce. And then lastly, at x equals 3, it's going to cross. So cross, and there we go. So these last two, you guys, example 3 and example 4, those are both examples of it being in standard form and graphing polynomials based off standard form. Alright, so that concludes today's lesson. See you guys later.